There was a poster on the wall. You probably remember it. A long horizontal strip of color, deep black at the edges, the sun burning yellow at the center, and 8 planets lined up in a neat, obedient row. Mercury closest to the fire, Neptune drifting cold and blue at the edge. Every planet labeled, every orbit drawn as a perfect circle. The whole universe, it seemed, had been tidied up and laminated for your convenience. That poster was not a lie. Not exactly. The planets are real. The sun is real. The distances, roughly, are accurate. But there was something embedded in that image that went deeper than the science. Something in the way it was presented, the way it sat on the wall without apology, without asterisk, without any suggestion that the picture might be radically, startlingly incomplete. It was presented as a portrait of the universe. It was not. It was a portrait of one tiny corner of one ordinary galaxy in a cosmos so vast and strange that no poster, no textbook, and no classroom has ever come close to capturing it. What you were handed was a map, and like all maps, it was a simplification. But this one had a particular quality that most maps do not. It made the blank spaces invisible. It didn't show you white regions labeled unknown. It showed you clean, ordered space and implied that the order was total, that scientists had measured the whole thing, that the story was essentially finished. And you believed it. Why wouldn't you? You were a child. The teacher believed it. The textbook confirmed it. The test asked you to memorize it. The system rewarded you for accepting it without question, and quietly discouraged the kind of curiosity that might lead you to ask what was just off the edge of the diagram. This is how the narrowing happens. Not through malice, not through conspiracy, but through the accumulated weight of institutional simplification. The way every generation of educators reduces the wild frontier of human knowledge into something that fits inside a semester, into something that can be tested, graded, and filed away. The universe, in that process, becomes domesticated. Its strangeness is sanded down, its open questions are quietly omitted, and the student, receiving this polished, confident version of reality, has no way of knowing what was left on the cutting room floor. What was left on the cutting room floor was almost everything interesting. The solar system poster showed you 5% of what exists, at most. The other 95%, the overwhelming majority of the universe by any measure, was simply not on the diagram. Not because it hadn't been discovered, not because scientists didn't know, but because the knowing was complicated, contested, and deeply uncomfortable, and there is no room for complicated, contested, and deeply uncomfortable on a classroom wall. So here, in the quiet of this moment, consider the possibility that the picture you were given was not a complete one, that the education you received about the cosmos was thorough in many ways and profoundly limited in others. Not because of a grand scheme to deceive you, but because of something almost more unsettling, because the institutions designed to teach you about reality were themselves more comfortable with a simplified version of it. The question worth asking now is simple. What was left out, and why does it matter so much that you find out? Consider for a moment what it would mean if someone handed you a map of an entire continent and quietly neglected to draw in the mountains. Not because there were no mountains, but because mountains were complicated, because they required extra pages, because the exam didn't cover them. You would navigate the continent with reasonable confidence until you encountered a range of peaks so enormous they blocked the horizon. And then you would understand, for the first time, that confidence is not the same thing as accuracy. Science has mountains that the textbooks forgot to draw. The first and most staggering is this. Everything that has ever been seen through any telescope, measured by any instrument, or touched by any human hand, every star, every planet, every ocean, every grain of sand, every atom of every living thing that has ever existed on Earth, accounts for approximately 5% of the total energy content of the universe. 5%. The other 95% is made of two things that science cannot see, cannot touch, and cannot fully explain. They have names, dark matter and dark energy, but a name is not an explanation. Naming something you don't understand is just a way of making the unknown feel temporary. That fact, that we are made of and surrounded by 5% of reality, does not appear prominently in school curricula. It is not drilled into students the way the periodic table is drilled, or the way the speed of light is presented as a tidy, comforting constant. It sits in a footnote, if it appears at all, offered as a curiosity, rather than the defining crisis of modern physics that it actually is. Then there is the Big Bang, the creation story of modern science, presented in classrooms with the quiet certainty of a documented historical event. A great explosion, a hot, dense beginning, everything expanding outward from a single point. Clean, tidy, dramatic. But here is what the textbook version omits. The Big Bang model does not describe the beginning of the universe. It describes what happened after the beginning, a tiny fraction of a second after something we cannot see, cannot model, and do not understand. The actual origin, the moment of moments, the cause behind all causes, remains completely, genuinely, officially unknown. Then there is the question of whether our universe is the only one. This is not a question reserved for science fiction. It is a serious, mathematically motivated area of theoretical physics, actively debated at the highest levels of cosmological research. The equations that describe the early universe, the same equations that have been verified by satellite data to extraordinary precision, strongly imply that our universe may be one of an uncountable number. Not might imply, strongly imply. The multiverse does not fall out of speculation. It falls out of the math. None of this is secret. These debates happen in peer-reviewed journals, at conferences, in the pages of books written by working physicists at major universities. The knowledge exists. It simply doesn't make it into the room where the solar system poster hangs. The uncomfortable truth is that science, as taught in schools, is often science as it existed 30 or 40 or 50 years ago, filtered through curriculum committees, simplified for standardized testing, and presented with a confidence that the researchers who actually work on these questions would never permit themselves. The men and women who study dark matter and dark energy do not speak with the certainty of a textbook. They speak with the careful, qualified language of people who know they are standing at the edge of something vast and poorly understood. The edge is where the real story begins. In 1998, the universe changed. Not the universe itself. The universe had been doing what it does for 13.5 billion years, without any need for announcement. What changed was the human understanding of it, and the change was so significant, so disorienting, so completely at odds with everything scientists thought they knew, that it should have made front-page headlines around the world and triggered a full revision of every astronomy textbook in print. Instead, it was absorbed quietly. A Nobel Prize was awarded in 2011. A few journal articles circulated, and the classroom poster remained unchanged. Here is what happened. Two teams of astronomers, working independently, set out in the late 1990s to do something straightforward, to measure how fast the universe was slowing down. Not whether it was slowing down, that was assumed. That was the expected answer, the answer that every model predicted, the answer written into the physics of gravity itself. Of course, the universe was slowing down. Everything that explodes eventually slows. The expansion of space, driven outward by the Big Bang, should have been decelerating under the mutual gravitational pull of all the matter in the universe, the way a ball thrown into the air slows before it falls. The astronomers pointed their telescopes at distant supernovae, exploding stars so bright they can be seen across billions of light-years, and used them as cosmic measuring sticks. The brightness of a supernova tells you how far away it is. The color of its light tells you how fast it's moving. Put those two pieces of information together, and you can map the history of cosmic expansion with remarkable precision. What they found did not fit the model. The distant supernovae were dimmer than they should have been. Not slightly dimmer, significantly dimmer, which meant they were farther away than any model had predicted, which meant the universe was not slowing down. The universe was speeding up. The expansion of space was accelerating. Something was pushing everything apart, not pulling it together, and that something had been growing stronger over billions of years, becoming more dominant as time passed, until it now controlled the fate of every galaxy, every star, and every atom of matter in the observable universe. They named it dark energy because naming it was all they could do. They had no explanation for what it was. They had no theory that predicted it. Its existence had been entirely invisible to physics until the moment the data refused to cooperate with the expected answer. This was not a minor correction to a minor equation. This was the discovery that an entirely unknown force, one that now constitutes roughly 68% of everything that exists, had been operating invisibly for the entire history of the universe without any scientist suspecting it was there. It overturned the foundational assumption that the universe was coasting toward stillness. It replaced that assumption with something far stranger, a cosmos actively accelerating toward a cold, dark, empty endpoint, driven by an energy that no one can see, explain, or even properly define. The Nobel Prize came 13 years later. The textbooks were not updated. The poster on the classroom wall showed the same 8 planets in the same neat row, and an entire generation of students continued to learn a version of the universe that had been quietly, irrevocably, officially superseded, not by a fringe theory, not by a rogue scientist, but by the most careful astronomical measurements ever made. The universe had been revised. Nobody told you. Imagine arriving at an enormous building, a structure so large it disappears into the clouds in every direction. The doors open, you step inside. A guide meets you in the entrance hall, walks you through a beautifully lit lobby with marble floors and tall windows, points out the details of the architecture, explains the history of the building, answers every question you ask with precision and warmth. After an hour, the guide leads you back to the entrance and says, "There, you have now seen the building." But you saw only the lobby. The rest of the building, 95 floors above you, corridors stretching in directions the lobby doesn't hint at, was never mentioned. The guide wasn't lying. The lobby is real. The marble is beautiful. But the tour was incomplete in a way that borders on deliberate misdirection. This is approximately what cosmology has done with the universe. Everything that has ever been directly observed, measured, catalogued, photographed, or touched by any instrument built by any civilization in the known history of intelligence on Earth represents roughly 5% of the total energy content of the universe. Not 90%, not 50, 5. The remaining 95% is divided between 2 substances, dark matter at around 27% and dark energy at around 68%, both of which are invisible to every instrument humanity has built, both of which interact with ordinary matter in ways that are only partially understood, and neither of which has been directly detected, despite decades of searching by some of the most sophisticated scientific minds and expensive experiments ever assembled. This is not a minority opinion held by alternative researchers at the margins of physics. This is the current consensus of mainstream cosmology, embedded in a model called Lambda CDM, the standard model of cosmology, which sits at the foundation of modern astrophysics and is accepted by the overwhelming majority of working scientists in the field. When physicists say they understand the universe, they mean they understand 5% of it with reasonable confidence and are deeply uncertain about the rest. The philosophical weight of this is genuinely difficult to absorb. Every thought ever thought, every object ever made, every relationship ever formed, every star ever born, and every star ever extinguished. All of this is made of the 5%. The world you can see, feel, and measure is a thin film stretched over an invisible ocean. The bulk of existence passes through you, through the room you are sitting in, through the Earth itself, interacting with ordinary matter only through gravity, leaving no trace that any detector has yet been able to capture. Dark matter does not emit light. It does not absorb light. It does not reflect or scatter it. It has no color, no temperature, no charge. Its presence is inferred entirely from its gravitational effects, the way it bends the path of light passing near it, the way its mass holds galaxies together in patterns that ordinary matter alone cannot produce. We know it is there the way you might know a strong wind is blowing, not by seeing the wind itself, but by watching what it does to the trees. Dark energy is stranger still, a force not of attraction, but of repulsion, woven into the fabric of space itself, growing in influence as the universe expands, pushing everything in every direction at an accelerating pace. It does not gather. It does not clump. It is everywhere equally, a property of space itself, rather than a substance moving through space, which makes it almost impossible to define in any intuitive terms, because nothing in ordinary experience behaves like it. 95% of everything, invisible, unnamed in any deep sense, and the lobby, meanwhile, is beautifully lit. In the 1970s, a woman at the Carnegie Institution of Washington was watching galaxies spin, and something she saw made no sense. Her name was Vera Rubin, and what she observed in the rotation of spiral galaxies should have been impossible, by every law of physics as it was understood at the time. The problem was elegant in its simplicity. When an object orbits a center of gravity, its speed depends on how much mass lies within its orbit. This is why the planets closer to the Sun move faster than those further away. Mercury races around the Sun in 88 days. Neptune takes 165 years. The pattern is predictable, calculable, confirmed by centuries of observation. It is one of the most reliable relationships in all of physics. Vera Rubin applied this same principle to spiral galaxies. She expected to find that stars at the outer edges of a galaxy, far from the massive center, would orbit slowly, just as Neptune orbits slowly far from the Sun. Instead, she found something that defied every expectation. The outer stars were orbiting at nearly the same speed as the inner ones. In some cases, they were orbiting even faster. The rotation curve was flat when it should have been falling. There was only one explanation that fit the data. A vast amount of invisible mass, far more than all the visible stars, gas and dust in any galaxy combined, must be distributed in a halo surrounding and extending beyond each galaxy, providing gravitational force at the outer edges where no visible matter existed. This invisible mass came to be called dark matter, and its presence was written clearly into the motion of every spiral galaxy Rubin measured. Her findings were not immediately celebrated. The scientific community resisted. Some of that resistance was legitimate skepticism. Extraordinary claims require careful verification, and the data needed to be confirmed across multiple independent observations. But some of it was less defensible. Rubin was a woman in a field dominated by men, at a time when women were not regularly invited to use major telescopes, not always allowed to use the facilities their male colleagues took for granted. She persisted. The data held. Galaxy after galaxy, the same pattern emerged. The universe was full of something invisible, something massive, something that made the motion of entire galaxies only possible because it was there. After Rubin's work, the search for the identity of dark matter became one of the central missions of modern physics. Underground detectors were built in mines deep below the Earth's surface, shielded from cosmic noise, listening for the faintest whisper of a dark matter particle passing through. Space telescopes were deployed to look for the subtle bending of light, gravitational lensing, caused by dark matter concentrations. Particle accelerators were directed toward collisions energetic enough, in theory, to produce dark matter particles that could then be measured in the aftermath. The search has been going on for more than 40 years. No direct detection has ever been confirmed. The leading theoretical candidate, a class of particles called WIMPs, weakly interacting massive particles, has been searched for with instruments of increasing sensitivity. Each time the sensitivity increased, the WIMP still wasn't found. Other candidates have been proposed: axions, sterile neutrinos, primordial black holes. Each has been investigated with rigor and precision. The silence continues. Something holds the galaxies together. Something vast and invisible wraps around every spiral structure in the observable universe, providing the gravitational scaffolding without which no galaxy could maintain its shape. Vera Rubin found it in the data. Physics confirmed it through 100 different measurements. And yet the thing itself, its nature, its composition, its origin, remains one of the deepest and most embarrassing mysteries in all of modern science. The ghost is real. It just won't be seen. Dark matter holds things together. Dark energy tears them apart. And of the two, dark energy is winning, by an enormous margin. If dark matter is the invisible scaffolding of the universe, dark energy is the invisible engine driving it toward a destination that no living thing will survive to witness. It is not a force in any conventional sense. It is not a particle, not a wave, not a field that can be isolated or directed. It appears to be a property of space itself, an intrinsic energy density that exists everywhere, equally, in every cubic centimeter of the vacuum, even in regions that contain no matter at all. As the universe expands and more space comes into existence, the total amount of dark energy increases, which accelerates the expansion further, which creates more space, which creates more dark energy. A feedback loop that has been running for billions of years and shows no sign of stopping. The consequence of this, followed to its logical end, is a universe that grows forever colder and emptier. Galaxies will drift beyond each other's visible horizons. Stars will burn out one by one, over timescales so vast that the current age of the universe is a rounding error by comparison. The last black holes will evaporate through a process called Hawking radiation, releasing one final whisper of energy into a universe that has become too cold and too diffuse for anything complex to exist. Physicists call this the heat death, a final state of maximum entropy, maximum disorder, minimum usable energy, where nothing happens anymore, not because anything is destroyed, but because nothing is different enough from anything else to drive any process forward. We are nowhere near that endpoint. The stars still burn, life still exists. But dark energy is the reason the universe will end the way it will, and it has been shaping the structure of the cosmos since long before any star was born. Now consider this. When physicists try to calculate how much dark energy should exist, using the best tools quantum mechanics provides, applying the equations to the known properties of the vacuum, they arrive at a number. That number, when compared to the actual measured density of dark energy in the universe, is off by a factor so enormous it is almost impossible to communicate. The theoretical prediction exceeds the measured value by roughly 10 raised to the power of 120. That is a 1, followed by 120 zeros. This discrepancy has been described by physicists as the worst prediction in the history of science. Not because the calculation was careless, but because it was done correctly, using the best available theory, and still produced an answer so cosmically wrong that it suggests something fundamental is missing from the entire framework of physics as currently understood. This is not a minor calibration problem. It is not the kind of error that a better measurement or a small theoretical adjustment will fix. It is a wall. It is the universe telling physics, with extraordinary bluntness, that the tools being used to describe it are missing something essential. The gap between what quantum mechanics predicts and what the universe actually does is the largest discrepancy between theory and observation in the history of scientific measurement. And yet, if you open a standard physics textbook, this problem is presented, if it appears at all, as a known challenge, a puzzle awaiting a solution, delivered with the calm tone of an exercise not yet completed. The vertigo that should accompany that number is smoothed away by institutional habit, by the professional necessity of continuing to function despite not knowing, by the quiet insistence of the academic culture that the problem will eventually yield. Perhaps it will. Science has solved apparently impossible problems before, and the history of physics is full of crises that resolved into breakthroughs. But this one is different in scale. This is not a crack in the edifice. This is a suggestion that the edifice itself is standing on ground that has never been properly mapped. Somewhere, in the unseen architecture of the cosmos, the real answer is waiting, and it is almost certainly stranger than anything currently imagined. There are two theories that between them describe everything physics has ever confirmed about the physical universe. They have each been tested to extraordinary precision. Together, they have made possible nearly every technology of the modern world. The GPS satellites that guide navigation, the MRI machines that look inside living bodies, the semiconductor chips that run every digital device, the nuclear power that lights entire cities. They are the most verified, most tested, most precisely confirmed frameworks in the history of human knowledge. They are also completely incompatible with each other. The first is general relativity, Albert Einstein's description of gravity, space, and time, published in 1915, and not substantially revised since. It describes a smooth, continuous universe in which mass curves the fabric of space-time, and that curvature is what we experience as gravity. The predictions of general relativity have been confirmed to astonishing degrees of accuracy. The bending of light around massive objects, the time dilation experienced by clocks moving at different speeds, the existence of black holes, the detection of gravitational waves rippling through the fabric of space, all of it predicted by Einstein's equations, all of it confirmed by measurement. The second is quantum mechanics, the description of how the universe behaves at the scale of atoms and subatomic particles, developed in the first half of the 20th century by a remarkable collection of minds including Bohr, Heisenberg, Schrödinger, and Dirac. At this scale, particles do not have definite positions or definite velocities until they are measured. They exist in clouds of probability. They can be in two places simultaneously. They can influence each other across any distance, instantly, in ways that seem to defy any conventional notion of space. Quantum mechanics describes this strange, probabilistic world with equations that have been verified to more decimal places than any other physical theory. Put these two theories side by side, and they describe the universe with breathtaking accuracy, each in its own domain. But push them into the same room and ask them to agree, and they fall silent. The mathematics produces nonsensical results, infinite values where there should be finite ones, indeterminate answers where there should be definite physics. This happens most dramatically in the description of black holes, where extreme mass and extreme density combine to create conditions where general relativity should and must be applied simultaneously with quantum mechanics. The math breaks, the equations stop being useful, something essential is missing, and no one knows what it is. This is not a secret. Physicists openly acknowledge it. The search for a theory of quantum gravity, a framework that unifies general relativity and quantum mechanics into a single coherent description, has been one of the central quests of theoretical physics for nearly a century. String theory, loop quantum gravity, causal set theory. Multiple competing frameworks have been proposed and developed, some requiring additional spatial dimensions, some requiring a fundamental discreteness to the fabric of space-time. None of them has produced a prediction that has been confirmed by experiment. None has achieved consensus. At the subatomic level, reality behaves in ways that have no analogy in everyday experience, and no comfortable translation into ordinary language. An electron does not travel from one place to another the way a thrown stone travels. It exists as a spread-out wave of probability until the moment it is detected, at which point the wave collapses and the electron is found to be somewhere specific. Before detection, asking where the electron is has no definite answer. It is not that the answer is unknown. It is that the question does not have a definite answer until the act of measurement forces one into existence. The foundation of everything, the bedrock layer of physical reality, is not made of solid, definite things, behaving in solid, definite ways. It is made of probabilities, uncertainties, and events that do not seem to fully exist until something interacts with them. The floor of the universe, at its deepest level, is not solid, and the discomfort that produces is not resolved by time or familiarity. Every physicist who has genuinely absorbed what quantum mechanics implies lives with a quiet, irreducible strangeness in the back of their mind. The question is what that strangeness means for the universe above it. There is an experiment so simple in its design and so devastating in its implications that physicists have been arguing about it for nearly a century without reaching agreement. It requires only a source of particles, a barrier with two narrow slits, and a detector on the far side. The particle involved, most famously, an electron, is fired at the barrier one at a time. What appears on the detector tells you everything about how the universe actually works at its most fundamental level, and what it tells you does not easily fit inside any ordinary picture of reality. When no measurement is made at the barrier, when nothing records which slit the electron passes through, the electrons build up a pattern on the detector that looks like interference. Bands of high and low intensity, the signature of two waves overlapping. This means the electron, a single particle, passed through both slits simultaneously and interfered with itself on the other side, as if it were a wave spread across space rather than a particle traveling through it. Now add a detector at the barrier, a device that can record which slit each electron passes through. The interference pattern vanishes. The electrons now land in two simple bands behind the two slits, as if each one chose a path and followed it like a normal particle. The wave behavior disappears the moment information about the electron's path becomes available. The act of gaining knowledge about the electron's trajectory changes what it does, not because the detector physically disturbs the electron in any significant way. The experiment has been refined to the point where the disturbance is negligible. The change happens because the information exists, not because of any physical push or pull. Observation, the acquisition of information, changes the physical outcome of an event at the fundamental level of reality. This is one of the most confirmed and least comfortable findings in all of science. It has been reproduced in thousands of experiments with increasing sophistication, with increasing isolation from external disturbance, and the result is always the same. The universe behaves differently when it is being watched. What this means has been debated since the experiment was first performed. The Copenhagen interpretation, the most widely taught response, says that quantum objects exist in superposition, in multiple states simultaneously, until measurement forces a single outcome. Before observation, the electron exists everywhere the wave function assigns it a probability of being. Observation collapses the wave function into a single, definite result. The question of what counts as an observation, what mechanism produces the collapse, and whether the collapse is a real physical process or merely a mathematical convenience, has never been definitively answered. The many-worlds interpretation takes a different position. The wave function never collapses. Every possible outcome of every quantum event occurs. The universe branches at each measurement into as many versions as there are possible results. The electron goes through the left slit in one branch and the right slit in another, and each branch continues forward as a separate, fully real universe. There is no collapse, no observer-induced change, only branching. In this picture, every decision ever made, every random event ever occurred, has produced a world for each possible outcome. The narrator does not choose between these interpretations, because physics has not chosen. What physics has confirmed, beyond any reasonable doubt, is that the act of observation, the act of a measuring device interacting with a quantum system in a way that produces information, changes what physically happens. Reality, at its most fundamental accessible level, is not independent of the process of knowing it. What that means for the relationship between consciousness and the physical world is a question that does not have a comfortable, settled answer. It simply sits there, in every physics textbook, described in careful technical language that rarely pauses to let the reader feel the full weight of what has been established. The universe behaves differently when it is observed. No one has ever fully explained why. In the final years of his life, John Wheeler, the physicist who named the black hole, who worked alongside Einstein and Bohr, who helped build the theoretical framework of quantum mechanics into a coherent body of knowledge, arrived at a conclusion that he pursued with quiet intensity until his death at 96 years old. He had spent decades studying the universe's deepest structure, and what he concluded was this: at its most fundamental level, the universe is not made of matter. It is not made of energy. It is made of information. He called it from bit. Every particle, every field, every event in the physical world, every it, derives its existence from a binary choice, from a yes or no answer to a physical question posed by observation. Reality, in Wheeler's final vision, is not a collection of things that exist independently and are then measured. It is a collection of answers to questions, brought into being by the act of asking them. Existence is not primary. Information is primary. This idea has not been disproven. It has not been widely adopted, but it has been taken seriously by a growing number of physicists and philosophers who find that information-theoretic frameworks resolve certain deep puzzles that purely matter-based frameworks cannot. The holographic principle, which emerged from the study of black hole thermodynamics and is now considered a serious proposal in theoretical physics, suggests that the information content of any region of space is proportional not to the volume of that region, but to the area of its boundary. The universe, in this picture, encodes three-dimensional reality onto a two-dimensional surface, the way a hologram encodes a three-dimensional image onto a flat plate. If reality is fundamentally informational, certain things follow. The universe has a minimum length, the Planck length, below which the concept of distance loses physical meaning, as if space itself is pixelated at an unimaginably small scale. The laws of physics are mathematical, not merely describable by mathematics, but constituted by it, running on mathematical rules with the same consistency and universality one would expect from a system operating according to a fixed code. The philosopher Nick Bostrom, in a paper published in 2003, formalized a question that had circulated informally for decades. He argued that one of three things must be true. Either nearly all civilizations capable of creating detailed simulations of reality choose not to run them, or nearly all such civilizations go extinct before reaching the technical capacity to do so, or we are, almost certainly, living inside such a simulation right now. The argument is not mystical. It is probabilistic. If even a small fraction of advanced civilizations run many detailed simulations, the number of simulated minds in existence would vastly outnumber the number of minds in base reality. The statistical probability of being one of the rare base reality minds rather than one of the countless simulated ones, becomes vanishingly small. Physicists including Michio Kaku, James Gates, and others have noted that the mathematical structure underlying the physical laws of the universe bears a striking resemblance to error-correcting code, the kind of mathematical structures used in computer science to ensure data integrity. Gates discovered these codes embedded in the equations of string theory, not placed there deliberately by any researcher, but emerging spontaneously from the mathematics. He described the experience of finding them as deeply unsettling. None of this proves the simulation hypothesis. None of it was intended to. But when the man who named the black hole spends the final decades of his career arguing that reality is made of information, when the mathematical infrastructure of the universe resembles computational code, when the smallest meaningful unit of space behaves like a pixel, the question stops being absurd. It becomes instead precisely the kind of question that a universe designed to be understood might leave lying quietly in plain sight. There is a story about the beginning of everything, and it goes like this. 14 billion years ago, there was nothing. Then there was everything. A singularity, a point of infinite density, exploded outward, and the universe was born in a flash of unimaginable heat and light. Space itself expanded, matter formed, stars ignited, galaxies assembled, planets cooled, and billions of years after the explosion, on one of those cooled planets, creatures evolved who could look back across time and piece together the story of how it all began. It is a magnificent story. It is also not quite right, and the ways in which it is not quite right are more interesting than the story itself. The Big Bang model is not a description of a creation event. It is a description of a state, the hot, dense, rapidly expanding condition of the early universe, and the evolution of that state forward in time. It begins at a moment when the universe was extraordinarily hot, extraordinarily dense, and expanding at an extraordinary rate. It describes what happened after that moment with remarkable precision. The cooling of the primordial plasma, the formation of the first hydrogen and helium atoms, the slow gravitational collapse of gas clouds into the first stars, the nuclear forging of heavier elements, the assembly of galaxies, the evolution of chemistry and biology across billions of years. All of this the model describes beautifully, verified at every step by observation. What the model does not describe is the beginning. The Big Bang is not a theory of creation. It is a theory of evolution, of how an already existing hot, dense state transformed over time into the universe as it is observed today. The question of what created that hot, dense state, what existed before it, what caused it to begin expanding, what determined its initial conditions, these questions lie outside the model entirely. The model does not say, and before that nothing. It says nothing at all about before that, because the mathematics breaks down at that point and becomes physically meaningless. This breakdown happens at what physicists call the Planck epoch, the first 10 to the minus 43 seconds of the universe's expansion, a span of time so brief that the entire age of the universe is inconceivably larger by comparison. Before that moment, the known equations of physics produce infinite values, what mathematicians call singularities, which is a technical way of saying the theory has reached the edge of its validity. The calculation stops working, the projector breaks. Think of it this way. Scientists have access to an extraordinarily detailed record of the universe's history, encoded in the light that has traveled across the cosmos and finally reached our instruments. They have mapped the cosmic microwave background, a faint glow of radiation that fills the entire sky, the afterglow of the hot early universe, and found it to be consistent with the Big Bang model, to 1 part in 100,000. The oldest light in the sky is a photograph of the universe when it was roughly 380,000 years old, and it matches the predictions precisely. But that photograph was taken a very long time after the beginning. Between the Planck epoch and the moment the light was released, an enormous amount happened. Inflation, the formation of the first particles, the annihilation of antimatter, the cooling of the primordial plasma, and the model traces all of it with increasing confidence as you move away from the origin. The origin itself remains behind a wall, not a wall of secrecy, a wall of physics. The mathematics that describes everything forward from the first fraction of a second stops working when pushed backward to the first moment. The beginning, the actual moment of beginning, if beginning, is even a meaningful concept, is inaccessible to current theory. What created the universe is not answered by the Big Bang. The Big Bang describes what the universe did after it existed. What made it exist at all is a question that no cosmological model yet answers, and one that some physicists suspect may require an entirely new framework of thought to even properly ask. If the origin of the universe cannot be explained by the standard model, then perhaps the question itself needs to be reframed. Perhaps the universe did not have an origin, in any absolute sense. Perhaps what appears to be a beginning was something else entirely, a transition, a bounce, a phase change in a process that has been running for longer than any single universe's lifetime. This is not a fringe proposal. It is the direction several of the most sophisticated minds in theoretical cosmology have chosen to explore. Paul Steinhardt of Princeton University and Neil Turok of Cambridge developed a model they called the cyclic universe, in which the Big Bang was not a unique origin event, but one of an infinite sequence. In their picture, the universe we inhabit exists on a three-dimensional membrane floating in a higher dimensional space, and periodically, on a timescale of trillions of years, this membrane collides with another membrane. Each collision releases an enormous burst of energy that looks, from within, exactly like a Big Bang. The universe expands, stars form, galaxies evolve, everything cools and spreads out over trillions of years, and then the cycle begins again. There was no first Big Bang. There has always been a universe, cycling through states of expansion and rebirth in an eternal rhythm. A different but related approach comes from loop quantum cosmology, a framework that attempts to apply quantum mechanics to space-time itself. In loop quantum cosmology, the singularity at the apparent beginning of the universe is resolved by quantum effects. The geometry of space-time cannot collapse to a true point because of a quantum mechanical repulsion that operates at the Planck scale. Instead of a singularity, there is a quantum bounce. The universe contracted to a minimum size and then rebounded outward. What we experience as the Big Bang was not a creation from nothing, it was a bounce from a prior contracting phase. Before our expanding universe, there was a collapsing one. Before that, presumably, another expanding phase. An endless sequence of contractions and expansions, each one linked to the next, through a quantum bridge that preserves certain information across the transition. Roger Penrose, one of the most celebrated mathematical physicists alive, a collaborator of Stephen Hawking and a Nobel laureate, has proposed yet another framework, which he calls conformal cyclic cosmology. In this picture, the infinite future of one universe and the Big Bang beginning of the next are mathematically equivalent, connected through a transformation of scale that strips away all meaningful distance and leaves behind a geometry that is indistinguishable from a new beginning. Penrose believes the echoes of the previous universe, he calls them Hawking points, might be visible in the cosmic microwave background as subtle circular patterns in the temperature distribution of the ancient light. There have been papers claiming to find these patterns. There have been papers disputing those claims. The debate continues. What all of these models share is the rejection of a unique beginning. In each case, the universe we inhabit is not the first one, and it will not be the last. Creation from nothing is replaced by transformation from something else, something prior, something connected, something that stretches the concept of time beyond the boundaries of any single cosmic cycle. The textbook does not mention any of this. The Big Bang stands in the curriculum as the beginning, full stop, presented with a confidence that the physicists who study it most carefully would never endorse. The question of what preceded the Big Bang, what caused it, and whether the concept of a unique beginning even makes sense, is one of the most actively contested in all of physics. The honest answer is not nothing or we know. The honest answer is that several different frameworks are being seriously pursued, none is confirmed, and the question remains entirely open. The word multiverse carries a particular burden. It has appeared in too many films, been used too casually in too many conversations, been invoked as metaphor in too many contexts where precision was not required. It feels by now like a cultural artifact rather than a scientific proposal, something belonging to the imagination rather than to the equations. This feeling is misleading. It should be set aside. The multiverse is not a theory that someone invented to explain an anomaly or to satisfy a philosophical preference. In its most scientifically motivated form, it is a consequence, almost a side effect, of a theory that was developed to solve a completely different problem. That theory is inflation. In the early 1980s, Alan Guth proposed that the very early universe underwent a period of exponential expansion. Not the gradual expansion described by the standard Big Bang model, but an extraordinarily rapid stretching of space that in a tiny fraction of a second expanded the universe by a factor of at least 10 to the power of 26. Inflation was proposed to explain several observational puzzles: why the cosmic microwave background is almost perfectly uniform in temperature across regions of the sky that should never have been in contact with each other, and why the large-scale geometry of the universe appears to be so precisely flat. Inflation solves both problems elegantly, and its predictions have been confirmed by satellite measurements to a high degree of precision. It is not fringe science. It is close to the mainstream. But inflation, once it starts, does not easily stop. In the equations that describe inflationary dynamics, the conditions that drive the exponential expansion are self-sustaining. Regions of space where inflation has ended, like the bubble of space that became our universe, are surrounded by regions where inflation continues, and those regions expand faster than the speed of light, rapidly becoming separated from our bubble by a growing gulf that nothing can cross. Other bubbles form in the inflating background. Each one begins a new universe with its own initial conditions, potentially its own physical constants, potentially its own laws of nature. The process never stops. It is eternal. This is not a feature someone added to inflation to make it more interesting. It falls out of the mathematics the way a shadow falls from a shape, automatically, without being asked for. If inflation happened, and the evidence is strong that it did, then eternal inflation is almost impossible to avoid, and eternal inflation generates an infinite multiverse of bubble universes, most of which we can never observe, because the expanding space between us and them prevents any signal from ever making the crossing. This creates a profound epistemological difficulty. If other universes exist but can never in principle be observed, can the multiverse be considered a scientific theory in any meaningful sense? This question divides physicists. Those who argue yes point out that the multiverse is a prediction of a theory, inflation, that has other testable predictions that have been confirmed. Those who argue no point out that a theory whose predictions cannot be tested is, by strict definitions, closer to philosophy than to science. Both positions are intellectually serious. What is not intellectually serious is the casual dismissal of the multiverse as a fantasy borrowed from comic books. It is a mathematically motivated consequence of the best-supported theory of the early universe, developed by serious physicists at major institutions, published in peer-reviewed journals, and debated at the highest levels of the field. Whether it is correct, and whether it can ever be confirmed, remain open questions. But it is not science fiction. It is science standing at the edge of what can be confirmed, looking out into the dark, and making its best calculation of what lies beyond. There are numbers that run the universe. Not metaphorical numbers, actual, measured values, fundamental constants that determine the strength of every force, the mass of every particle, the rate at which every process unfolds. These constants are not derived from any deeper theory. They are not explained by any known principle. They simply are what they are, measured by experiment to great precision, and then inserted into the equations as given facts. The speed of light, the gravitational constant, the strength of the electromagnetic force, the mass of the electron, the cosmological constant, a handful of others. Change any of these by even a small fraction, and the universe becomes uninhabitable. Not uninhabitable in the sense that it becomes slightly uncomfortable for life. Uninhabitable in the sense that it contains no stars, no atoms, no structure of any kind. Consider the strong nuclear force, the force that holds the nuclei of atoms together. If it were slightly weaker, protons and neutrons would not bind to each other, and no atomic nucleus heavier than hydrogen would exist. Every element in the periodic table beyond hydrogen, the carbon that makes up organic chemistry, the oxygen in every breath, the iron at the core of every red blood cell, requires nuclei held together by the strong force. A universe with a slightly weaker strong force is a universe of pure hydrogen gas, drifting in permanent darkness, forever. Consider instead What would happen if the strong force were slightly stronger? In the first minutes after the Big Bang, when the universe was hot enough for nuclear fusion, hydrogen would have fused so efficiently into helium and heavier elements that essentially no hydrogen would remain. No hydrogen means no water. No hydrogen means the most common fuel for stars, the fuel that has been burning in the sun for 4.5 billion years, would not exist. A universe with a slightly stronger strong force is a universe without stars, or with stars that burn so briefly that no planet has time to cool, no chemistry has time to develop, no complexity of any kind has time to emerge. Now consider the cosmological constant, the value of dark energy density. The observed value is extraordinarily small. Not zero, but close to zero by any natural standard. If the cosmological constant were even modestly larger, the universe would have expanded so rapidly in its early history that no galaxies could have formed. The gas that would have become stars and planets would have been dispersed into the void before gravity could gather it. If the cosmological constant were negative rather than positive, the universe would have collapsed back on itself long before stars could form. The precision required for the cosmological constant to permit structure to exist is roughly 1 part in 10 to the power of 120. That is not a rounding error. It is a calibration so fine that it has no natural explanation within the current framework of physics. It simply is what it is, and what it is happens to permit galaxies, stars, planets, chemistry, and everything that follows from those things. Physicists call this fine-tuning, and they argue vigorously about what it means. Some say it means nothing. The universe is what it is, and we are here because if it were different, we would not be here to ask about it. Some say it points toward a multiverse. If infinite universes exist with randomized constants, it is expected that some will have life-permitting values. Some say it suggests a designer, something or someone outside the universe that selected these parameters from among the infinite possibilities. All three positions have serious problems. None of them has won the argument, and the argument has been going on, in increasing technical sophistication, for decades. What is clear is this. The universe is balanced on specifications so precise that they demand an explanation, and the explanations that have been offered are each, in their own way, more unsettling than the problem they were meant to solve. The fine-tuning problem stands at an unusual intersection. It is a legitimate scientific puzzle that also touches the deepest questions of meaning, purpose, and existence. Because of this, the answers proposed to explain it come from different directions, from physics, from philosophy, from theology, and none of them can be easily dismissed, and none of them fully satisfy. The first answer is pure chance. Perhaps the constants are what they are for no reason. Perhaps the universe has no explanation behind its calibration, no designer who selected these values, no deeper law from which they can be derived. They are what they are, and the only reason we are here to notice is that if they were different, we wouldn't be. This argument, sometimes called the anthropic selection effect, is logically impeccable. It cannot be disproven, but it purchases logical validity at the cost of philosophical emptiness. It explains the fine-tuning by saying, there is nothing to explain. The appearance of design is an illusion created by the fact that only observers in fine-tuned universes exist to observe. The second answer is the multiverse. If an enormous or infinite number of universes exist with different values of the fundamental constants, as eternal inflation predicts, then no calibration is required. The lottery is played an infinite number of times, and inevitably some universes will win. Ours is one of the winners, and we exist in it because the losers produce no life to ask questions. This answer is scientifically motivated and logically coherent, but it has a significant cost. It places the explanation in a domain that is in principle unobservable. The other universes, if they exist, are beyond any horizon we can ever cross. A theory that explains everything and predicts nothing observable walks a narrow line between physics and metaphysics. The third answer is design, the hypothesis that the constants were selected by an intelligence or a process outside the universe, one with the capacity and the motivation to set the initial conditions precisely enough for complexity and life to emerge. This answer is the most culturally familiar and the most philosophically dangerous. It solves one mystery by introducing a larger one. What is the nature of the designer? Where did it come from? Who designed the designer? The regress it creates is as deep as the problem it was meant to resolve. And it is the only answer of the three that lies entirely outside the scope of scientific investigation. Because science, by its nature, can only address questions about the physical universe and not about what might exist outside it. None of these answers is satisfying. All three are held by serious thinkers. The debate between them has been running for decades and shows no sign of resolution. What is worth noticing is that all three point in the same direction, toward an admission that the universe, as presently understood, does not explain itself. The calibration of the constants is a fact. The explanation for that calibration is absent. The curriculum presents the constants as given, as though the precision of their values were unremarkable, as though the question of why they are what they are had never occurred to anyone. It has occurred to everyone who has looked carefully. The question just doesn't fit on a test. What is striking, from a certain perspective, is how rarely this problem is communicated to the general public with anything approaching its true weight. The fine-tuning of the universe is not an observation that sits quietly at the edge of physics. It is an observation that sits at the center of physics' deepest unresolved problems, and the silence around it in public education is itself a kind of answer, not about the universe, but about the limits of what institutions are comfortable discussing. In 1973, at a conference in Krakow, held to honor the 500th anniversary of Copernicus's birth, an astrophysicist named Brandon Carter introduced a concept that has been generating controversy ever since. He called it the anthropic principle, and he introduced it as a corrective to what he saw as an overcorrection in modern scientific thinking. The Copernican revolution had taught science a valuable lesson. Do not assume that humanity occupies a special place in the universe. Earth is not the center. The sun is not the center. Our galaxy is not special. Our location in the cosmos is typical, unremarkable, average by any measure. This insight, sometimes called the Copernican principle or the principle of mediocrity, had been enormously productive, driving astronomers away from geocentric biases and toward a more honest assessment of humanity's cosmic position. Carter's point was that the principle had been applied too broadly. There are cases, he argued, where our position in the universe is not typical. Specifically, it is not typical because we exist. The universe must have had properties that permitted observers like us to exist, because if it didn't, there would be no one here to observe it. This is the weak anthropic principle, and in its basic form, it is nearly a tautology. Of course, the universe we observe is compatible with our existence, because we exist and are observing it, but it becomes useful when applied to specific questions. Why does the universe have the age it has? Because we exist, and we could not exist in a universe younger than several billion years, or older than a certain point when stars begin to fail. The strong version goes further, and is far more controversial. It proposes that the universe must develop conditions for the existence of observers at some stage. Not merely that it happens to permit observers, but that it must. This is close to teleology, the idea that the universe has a direction, a purpose, an end it is working toward, and most scientists recoil from it, because teleology has historically been associated with religious rather than scientific thinking. Whether that reaction is always justified is a question worth asking. But the most unsettling application of anthropic reasoning is not the principle itself. It is an argument first formalized by Brandon Carter and later developed by philosopher Nick Bostrom and others, known as the doomsday argument. It goes like this. If you assign a random position to yourself within the sequence of all humans who will ever live, the most likely position is somewhere in the middle. Currently, roughly 100 billion humans have been born. If you are typical, you are somewhere near the midpoint of human history, which would imply that roughly 100 billion more humans will be born before the species ends. On the timescales of modern civilization, that is not a reassuring number. It suggests that the long, expansive human future imagined by optimistic futurists, a civilization spreading across the galaxy over millions of years, is unlikely. If it were likely, you would be extraordinarily early in human history, a statistical outlier of almost impossible improbability. The argument has been challenged on technical grounds, and those challenges are worth reading, but it has never been definitively refuted, and 50 years of philosophical scrutiny have not produced a consensus dismissal. It keeps returning, quiet and uncomfortable, a piece of reasoning that uses nothing but logic and statistics, and arrives somewhere most people would rather not go. Fine-tuning is, in the end, not just a puzzle about physics, it is a mirror. When you look at the precision with which the universe is calibrated to permit your existence, and then apply careful reasoning to what that precision implies about your place in the timeline of the beings it produced, the universe looks back with an expression that is difficult to interpret and impossible to ignore. It was lunchtime in the summer of 1950, and Enrico Fermi, one of the architects of the nuclear age, a physicist of extraordinary range and intuition, was sitting with colleagues at Los Alamos, New Mexico. The conversation had turned, as conversations at that table often did, to the broad and speculative. Someone had mentioned a recent cartoon about flying saucers, a light-hearted cultural artifact of a generation that had just learned what atoms could do and was beginning to wonder what else might be out there. Fermi listened, said little, and then, seemingly out of nowhere, asked a question that has haunted science ever since. Where is everybody? The question sounds casual. It was not. Behind it was a chain of reasoning that Fermi, characteristically, had assembled in the time it took his colleagues to reach for their coffee. The Milky Way galaxy is roughly 13 billion years old. Stars far older than our Sun, billions of years older, have had time to develop planetary systems, produce chemistry, generate biology, and permit the evolution of intelligence. Even with conservative assumptions about the probability of life arising and the probability of that life developing technology, the numbers suggest that civilizations older than ours by millions of years should exist in the galaxy in significant numbers. A civilization with even a modest head start on humanity, 1,000,000 years, a fraction of the galaxy's age, would have had time to colonize the entire Milky Way many times over, even using ships that travel at a tiny fraction of the speed of light. Yet there is nothing, no signals, no megastructures blocking starlight in ways that suggest engineering on a stellar scale. No probes, no transmissions, no galactic infrastructure leaking radiation into space. 70 years of deliberate listening, using radio telescopes pointed at thousands of candidate stars, have produced a uniform, unbroken silence, broken only by one anomalous event in 1977 that was never explained and never repeated. The Drake equation, developed by astronomer Frank Drake in 1961, provides a framework for estimating the number of communicating civilizations in the galaxy at any given time. It multiplies together estimates for the rate of star formation, the fraction of stars with planets, the fraction of those planets capable of supporting life, the fraction where life actually develops, the fraction where intelligence emerges, the fraction where communication technology is developed, and the average lifespan of a communicating civilization. The equation does not produce a single answer. It produces a range, entirely dependent on the values assigned to each factor, most of which are deeply uncertain. But even the most pessimistic plausible inputs tend to produce numbers greater than 1. The galaxy should not be empty, and yet it appears to be. This is not a small discrepancy. It is not the kind of anomaly that might be explained by a missed measurement or a slightly wrong estimate of some secondary factor. It is a gulf between what the physics and statistics of a 13-billion-year-old galaxy imply and what the sky actually shows. Either the assumptions underlying the Drake equation are far more pessimistic than they appear, or something is happening, something that prevents civilizations from becoming visible, from expanding, from persisting, that we have not identified. The silence is not a neutral observation, it is data, and like all data, it requires an explanation. The explanations that have been proposed range from the comforting to the genuinely terrifying, and the most honest thing that can be said is that none of them is definitively ruled out, and none of them is definitively confirmed. What Fermi's question does, at its best, is force a confrontation with the scale of the mystery. We are a species that has been broadcasting radio waves into space for roughly a century. We have had spaceflight for less than a human lifetime. We are, cosmologically speaking, an infant civilization, a brief flicker in a galaxy old enough to have produced and extinguished millions of civilizations before our planet formed. And yet we are here, and the galaxy is quiet, and the question that a physicist asked over lunch 70 years ago has never been answered to anyone's satisfaction. The silence is absolute, and absolute silence, in a universe this old and this vast, is the strangest possible answer. The Fermi paradox does not leave a thoughtful mind undisturbed. Once you have genuinely absorbed it, once the silence of the sky has stopped feeling like the absence of a problem and started feeling like the presence of one, the mind searches for an explanation. Several have been proposed, and they occupy a wide emotional spectrum. At the reassuring end of the spectrum, the rare Earth hypothesis suggests that life capable of producing technology requires an extraordinarily specific combination of conditions: the right type of star, the right orbital distance, the presence of a large moon to stabilize axial tilt, the presence of a gas giant to deflect asteroids, the right planetary chemistry, the right geological activity. Perhaps these conditions, each individually modest in their probability, combine to produce a joint probability so small that technologically capable life is genuinely rare, perhaps unique to Earth. In a galaxy of 400 billion stars, this is not impossible. The galaxy could be silent simply because we are the first. A stranger but equally serious proposal is the zoo hypothesis, which reverses the question entirely. Perhaps advanced civilizations do exist. Perhaps they know we are here. And perhaps they have agreed, for reasons of policy or ethics or scientific caution, not to interfere with us. Earth, in this picture, is a nature preserve or a controlled experiment, and the absence of contact is not an absence of observers, but an abundance of restraint. The silence is intentional. We are being watched from a careful distance. More technically motivated is the transcension hypothesis, which argues that advanced civilizations do not expand outward into space. They expand inward, into the computational and virtual spaces that physics permits. A civilization a million years more advanced than ours may long ago have migrated into substrate-independent existence, running on computational architectures at scales far below what any telescope could detect. They are not out there in the stars. They are in the quantum foam, in places smaller than atoms, running processes that leave no electromagnetic signature that any radio telescope would recognize. And then there is the Great Filter. Proposed by economist Robin Hanson in 1998, the Great Filter argues that somewhere on the path from a planet with the right chemistry to a civilization that has spread beyond its home star, there is an obstacle so severe that virtually no species crosses it. A step in the development of life or civilization so unlikely, so dangerous, or so catastrophic that the galaxy is littered with civilizations that attempted it and failed, and the silence is the sound of their failure. The question that makes this argument genuinely frightening is not whether the Great Filter exists. The silence of the galaxy is strong evidence that something filters civilizations out. The question is where it lies. If the Great Filter is behind us, if the hard step was the origin of life, or the evolution of complex multicellular organisms, or the development of language, then we have already passed it. We are the rare survivors, and the future, while not guaranteed, is open. If the Great Filter is ahead of us, then virtually every civilization that has reached our current level has subsequently been destroyed or silenced by something we have not yet encountered, something waiting in the future of every technological civilization, perhaps nuclear weapons, perhaps artificial intelligence, perhaps a technology not yet imagined, waits ahead, and the silence of the sky is a cemetery. Every time astronomers discover the chemical building blocks of life somewhere new, in the atmosphere of Venus, in the water of Enceladus, in the organic chemistry of a distant exoplanet, two emotions are warranted simultaneously: wonder, because life's ingredients are widespread, and quiet dread, because widespread ingredients make the Great Filter more likely to lie ahead rather than behind. The silence continues, and no explanation for it is comfortable. On the night of August 15, 1977, a radio telescope in Delaware, Ohio, was sweeping across the sky, as it had done many times before, a patient, automated scan of the heavens, looking for anything unusual in the radio spectrum. The telescope was called Big Ear, and it belonged to Ohio State University, and it had been running as part of the SETI project, the search for extraterrestrial intelligence, for years without finding anything that justified the name. That night, something changed. The telescope swept across a region of sky in the direction of the constellation Sagittarius. In the data it collected, at a frequency of 1,420 megahertz, the precise frequency of hydrogen radiation, long considered by SETI researchers to be the most logical choice for an interstellar beacon, because hydrogen is the most abundant element in the universe, and any spacefaring civilization would know its spectral signature. The telescope detected a signal, not a faint whisper, a burst of radio energy 30 times stronger than the background noise of space, lasting exactly 72 seconds, the precise window during which the telescope's beam could remain on a fixed point in the sky as the Earth rotated. The signal had the exact characteristics that SETI researchers had said for decades they were looking for. Several days later, an astronomer named Jerry Eman was reviewing the printouts of that night's data, long sheets of computer paper covered in alphanumeric codes representing signal intensities. Most of the page was ordinary, the unremarkable static of the radio universe. Then, standing out from the background with a clarity that required no interpretation, was a sequence of characters so striking that Eman reached for a red pen and wrote a single word in the margin, circling the sequence. Wow. The word became the name. The wow signal has been discussed, analyzed, and searched for ever since. Dozens of follow-up observations have been made using more powerful equipment, pointing at the same region of sky. The signal has never been heard again. No natural astrophysical source has been identified that could produce a signal with those specific characteristics: the right frequency, the right bandwidth, the right intensity profile, the right duration. Some researchers have proposed comets as an alternative explanation. The proposal generated controversy and significant skepticism. Others have suggested the signal was a reflection of terrestrial radio interference from an unusual atmospheric or orbital source. No explanation has been confirmed. What exists, 49 years later, is a single data point. One night, in one region of sky, a radio telescope detected something that matched, with remarkable precision, what a deliberate interstellar transmission would look like. The signal was real. The instrument was functioning correctly. The frequency was exactly the one that any rational engineer designing an interstellar beacon would choose, and it has never been explained. Sit with that for a moment. Not with the conclusion that it was extraterrestrial. That conclusion has not been established, but with the fact of the uncertainty. In a universe where the silence is supposed to be total, where 70 years of listening have produced nothing, there exists one night, one region of sky, one unexplained event that a careful astronomer looked at and could only mark with the most immediate and honest response available to him. The word wow is not a scientific conclusion, but it is a human one. It is what happens when a mind accustomed to silence and negative results is suddenly confronted with something that doesn't fit the expected pattern, something that sits in the data without explanation, without echo, without resolution. Whether the wow signal was a cosmic accident, an instrument artifact, or something else entirely, it represents a moment when the silence of the sky was interrupted, and the interruption has never been accounted for. That is a fact. The interpretation of that fact remains, like the signal itself, open. There is a question that neuroscience, for all its remarkable progress, cannot answer. It is not a question about how the brain processes information. Science has made extraordinary strides in understanding how neurons fire, how signals travel along axons, how neurotransmitters cross synaptic gaps, how different regions of the brain coordinate different functions. The mapping of neural activity has become astonishingly precise. Scientists can watch a living brain think, remember, feel fear, recognize faces, make decisions. The machinery is becoming understood. But the question is not about machinery. The question is about experience. Why does anything feel like anything? When you look at the color red, there is a physical process. Light of a certain wavelength strikes the retina. Signals travel up the optic nerve. The visual cortex activates in characteristic patterns, and you say red. All of that is explicable. Neuroscience can trace the path from photon to perception in increasingly fine detail. But in the middle of that chain, somewhere between the neural activation and the verbal report, something else is happening, something that no description of neural activity has yet captured. There is the redness of red, the quality of the experience itself, the way it feels, from the inside, to see that color. This is not the same as the mechanics of color perception. It is something additional, something that the mechanics do not account for. It is what philosophers call qualia, the subjective, felt quality of experience. David Chalmers, a philosopher at New York University, gave this gap its name in 1995. He called it the hard problem of consciousness. distinguishing it from what he called the easy problems. Not easy in any colloquial sense, but tractable in principle. The easy problems are the ones neuroscience can in principle solve. How does the brain integrate information? How does it focus attention? How does it produce behavior in response to stimuli? These questions are difficult, but they have the character of engineering problems. They can in principle be answered by understanding the mechanism in sufficient detail. The hard problem is different. Even a complete, perfectly detailed description of the neural mechanism of color perception would leave a question unanswered. Why does that mechanism give rise to an experience at all? Why isn't it all just processing, happening in the dark, without any felt quality? Why is there something it is like to be a human brain, rather than nothing? This question has not been answered. It has been debated intensely since Chalmers named it, and before that it circulated under different names in philosophy for centuries. The most common response from the scientific community is some version of, the experience is what the brain computation is. Consciousness is what complex information processing feels like from the inside. When the mechanism is fully understood, the experience will be explained. This answer may be correct, but it has a structure that philosophers find suspicious. It asserts that the explanation exists without providing it, and it assumes that a description of mechanism is equivalent to an explanation of experience in a way that has never been demonstrated. Every detailed account of neural activity produced so far describes a third-person process, something observed from the outside. Experience is first-person, something had from the inside. How the third-person description gives rise to the first-person fact is precisely the problem, and saying the description is complete does not bridge that gap. The brain is arguably the most complex structure in the known universe, and the product of its operation, subjective experience, the felt quality of being alive, is simultaneously the most intimate fact about existence, and the one least captured by any scientific framework currently available. That gap is real. It is not a gap in popular understanding or in public communication. It sits in the center of the most rigorous philosophical and scientific literature on mind, and the people who work on it most carefully are the least likely to claim it has been solved. The hard problem of consciousness does not exist in isolation. It sits uncomfortably close to another unresolved question, the quantum measurement problem, and the proximity of these two mysteries has led some of the most creative minds in physics and philosophy to wonder whether they are, at some level, the same problem. Return to the double-slit experiment. An electron behaves like a wave until it is measured, at which point it behaves like a particle. The act of measurement, the acquisition of information about the electron's path, changes its physical behavior. Physicists have spent decades trying to define what counts as a measurement. The most careful modern formulations say that a measurement is simply any physical interaction that creates a correlation between the measured system and a measuring device, and that no consciousness is required. A detector does the job. Even a molecule bumping into the electron does the job. But this answer, while probably correct in practice, does not fully dissolve the question. It pushes the problem back one level. What counts as a physical interaction that creates a meaningful correlation? At what point in the chain, from electron to detector, to amplifier, to digital readout, to human perception, does the quantum superposition resolve? The mathematics of quantum mechanics does not specify this. It describes the wave function evolving smoothly according to the Schrödinger equation, and it describes the outcome of a measurement. But the transition between those two descriptions, the collapse, is not derived from any equation. It is an assumption added to the theory to match observation. Into this gap, physicist Roger Penrose and anesthesiologist Stuart Hameroff introduced a proposal that remains among the most controversial in modern science. They argued that consciousness arises from quantum computations occurring in structures called microtubules inside neurons, protein lattices that form the cytoskeleton of the cell. In their framework, the brain is not merely a classical computer made of neurons. It is a quantum device that performs computations at a level where quantum mechanics and general relativity meet, and consciousness is the subjective experience of these quantum processes. The collapse of the quantum wave function, they argued, is not triggered by any external measurement. It is an objective physical process, what they called objective reduction, that occurs when the quantum superposition becomes large enough to create a measurable difference in the curvature of space-time. The theory is controversial. Many neuroscientists consider the brain too warm and wet for quantum coherence to survive long enough to be relevant. Many physicists find the proposal speculative, but it has not been definitively refuted, and it has the quality of addressing both the hard problem and the measurement problem with the same mechanism, which, if true, would represent an extraordinary unification. Meanwhile, mathematician and physicist Max Tegmark has argued that consciousness is a state of matter, a phase of physical information processing with specific, measurable properties, and that a rigorous science of consciousness is possible within a purely physical framework. Building on the work of neuroscientist Giulio Tononi, Tegmark connects consciousness to a quantity called integrated information, denoted by the Greek letter phi. A system has consciousness, in this framework, to the degree that its information processing cannot be decomposed into independent parts, to the degree that the whole is more than the sum of its components. High phi means rich experience. Low phi means dim or absent experience. In this picture, consciousness is not unique to biological brains. It is a property that any sufficiently integrated information processing system can have, in varying degrees. The question of whether the universe itself, as the largest and most integrated information processing system conceivable, has any form of experience, becomes, within this framework, a quantitative rather than a mystical question. The answer is not yet known, but the question, asked carefully and with mathematical precision, turns out to be a legitimate one. Carl Sagan said it quietly, almost in passing, in a way that made it sound like poetry. He said, "We are a way for the cosmos to know itself." He said it as a rhetorical flourish, a reminder that the atoms of which we are made were forged in the hearts of stars, that the universe had produced, through billions of years of physical and chemical and biological evolution, beings capable of looking back and understanding the process that created them. It was beautiful. It was moving, and most people who heard it took it as metaphor. Some philosophers and physicists are now arguing it may be a literal description. Cosmopsychism, the philosophical position that the universe itself is the fundamental bearer of consciousness, and that individual minds are expressions or aspects of that universal consciousness, rather than isolated sparks produced by biological accident, has moved in recent decades from the edges of academic philosophy toward a position of serious debate. It is not mysticism. Its contemporary proponents include Philip Goff at Durham University and Bernardo Kastrup, both of whom have published extensively in mainstream philosophical venues, building arguments from the very problems that physicalist accounts of consciousness have struggled to resolve. The argument, in its most rigorous form, starts from the hard problem. If consciousness cannot be derived from purely physical description, if there is always a gap between the mechanism and the experience, then perhaps the relationship between mind and matter needs to be reversed. Perhaps consciousness is not what matter produces. Perhaps matter is what consciousness does. In this view, the universe is not a collection of unconscious particles that somehow, in sufficient complexity, generate experience. It is something more like an experience that, at certain scales and in certain configurations, produces the appearance of discrete material objects. This reversal does not resolve all philosophical problems. It introduces new ones. But it has a quality that materialist accounts lack. It does not face the hard problem, because in a universe where consciousness is primary, the existence of experience is not something to be explained. It is the starting point. Now consider this alongside integrated information theory. If consciousness is proportional to the integration of information, and if the universe as a whole is the most integrated information system that exists, every part connected to every other part through the laws of physics, every event constrained and influenced by the entire history and structure of the whole, then the universe has a phi value larger than any subset within it. In the formalism of IIT, this would make the universe more conscious, not less, than any of its parts. This is not a conclusion most physicists are ready to accept. It is a conclusion that emerges, with a certain uncomfortable logic, from frameworks that were developed by serious researchers attempting to solve the problem of consciousness on scientific terms. Sagan's line was, "We are a way for the cosmos to know itself." If cosmopsychism is correct, the phrasing needs only the most minor adjustment. The cosmos is not using us as instruments to achieve knowledge it would otherwise lack. The cosmos is knowing itself through us, because knowing is what it does, because experience is not a product of the universe but its most fundamental nature, because every star that burns and every mind that wonders is the universe doing the only thing it has ever been doing. That is a large claim. It is held by serious thinkers. It has not been proved. It has not been disproved. And it sits, quietly, at the intersection of the hardest problem in philosophy and the deepest mystery in physics, waiting for the kind of mind willing to hold both questions simultaneously without forcing a premature resolution. The cosmos stirs. The cosmos asks. Perhaps that is the same thing. Before there were telescopes, there were eyes. And before there was artificial light to drown the night sky in comfortable orange glow, there were people who lay down in darkness and stared upward for hours, for years, for generations, memorizing the movement of every light in the sky with a patience and precision that the modern world has largely lost the capacity to appreciate. They were not primitive. The word primitive applied to people who tracked the precession of the equinoxes across centuries and built monuments aligned to within fractions of a degree of true astronomical north, is not a scientific judgment. It is a reflex of condescension applied by one civilization to another without looking carefully at the evidence. Look carefully, and the evidence is extraordinary. Stonehenge, on the Salisbury Plain of England, was constructed over several phases, beginning approximately 5,000 years ago. Its main axis is oriented with remarkable precision toward the point on the horizon where the sun rises at the summer solstice, a fact noticed and studied for centuries. But recent archaeoastronomical research has revealed additional alignments, lunar standstills, the most extreme northern and southern positions of the moon's rise and set across its 18.6-year cycle, encoded in the positioning of the outer ring with precision that required systematic observation over decades. This was not accidental architecture. It was an observatory built from stone by people who had been watching the sky long enough to understand cycles that require at least a generation of careful observation to detect. The Great Pyramid of Giza is oriented to true north, not magnetic north, which shifts over time, but the geographic North Pole, with an accuracy of 0.05 degrees. For comparison, the Paris Observatory, built in the 17th century with instruments unavailable to ancient Egypt, is aligned less precisely. The shafts inside the pyramid's chambers point to specific stars as they appeared in the Egyptian sky 4,500 years ago. Whether this was engineering precision for purely structural reasons or astronomical intentionality remains debated. What is not debated is the precision itself. The Maya of Mesoamerica developed a calendar system of extraordinary sophistication. Their long count calendar tracked time across cycles of millions of years. Their astronomical tables predicted the appearances of Venus, the most irregular of the visible planets, with an accuracy that required observations accumulated across many generations. Their eclipse tables, preserved in the Dresden Codex, allowed the prediction of lunar eclipses with an accuracy that modern astronomers have confirmed by calculating backward. They did not have electronic instruments. They had time, patience, and a cultural tradition that treated the sky as the most important text in existence. In the Vedic astronomical tradition of ancient India, texts composed thousands of years ago describe a value for the precession of the equinoxes, the slow wobble of Earth's axis that shifts the position of the stars over 26,000 years. That is close to the modern measured value. How a culture without telescopes or calculus arrived at this figure through naked eye observation alone remains a genuine question. These are not the achievements of people who did not understand the sky. They are the achievements of people who understood the sky differently, through accumulation, through patience, through a relationship with celestial cycles that modern society has largely abandoned in exchange for electric light and the comfort of treating the night as something to be illuminated rather than observed. What they knew, and what they encoded in stone and text and calendar, was not everything. But it was far more than the school version of ancient history typically suggests. There is a temptation, when drawing parallels between ancient wisdom and modern science, to overstate, to find design in coincidence, to mistake metaphor for measurement, to allow the romance of convergence to override the discipline of evidence. That temptation should be resisted. The parallels between ancient cosmological frameworks and modern physics are interesting, not because they prove that ancient civilizations had access to knowledge they should not have had, but because they suggest that certain deep intuitions about the nature of reality have been arrived at independently, from different directions, through different methods, across widely separated cultures and centuries. The Hindu concept of Brahman describes an ultimate, undifferentiated reality underlying all phenomena, a single field from which all apparent distinctions arise and into which they ultimately dissolve. This is not the same as a quantum field. The analogy is philosophical, not technical. But the structure of the idea, that surface appearances of separate, distinct objects mask a deeper unity, resonates with the way modern physics describes the world at its most fundamental level, where particles are excitations of fields, where fields are aspects of a unified framework, where the apparent discreteness of matter dissolves into continuous mathematics. Hindu cosmological time is measured in units that dwarf any Western religious framework. A single day of Brahma, one cosmic cycle of creation, existence, and dissolution, lasts 8.64 billion years. A full life of Brahma spans 311 trillion years. These numbers were not derived from observation in any way that science can reconstruct, but they reflect an intuition that the universe operates on timescales that make human history a rounding error. An intuition that Western science arrived at only in the 20th century, when geological and cosmological dating gave the universe its true age. The Buddhist concept of shunyata, often translated as emptiness, does not mean nothingness. It means that all phenomena lack inherent, independent existence. Every object, every event, every identity arises through dependent origination, through its relationships with other phenomena, and has no self-existence apart from those relationships. This is not the same as quantum field theory, where particles have no existence, independent of the fields that produce them and the measurements that define them. But the philosophical structure, the insistence that no thing stands alone, that existence is relational rather than intrinsic, is striking in its resonance. The Andean cosmological tradition of the Inca describes a universe that is alive and responsive, a cosmos in which mountains, rivers, stars, and human beings participate in a continuous web of relationship and reciprocity. The sky is not a backdrop, it is an actor. This framework, dismissed as animism by European colonizers, describes a world in which the boundary between observer and observed is not fixed, in which the universe is not indifferent to the beings within it. The parallels to consciousness-based cosmologies are inexact but suggestive. None of these traditions require defending as literal science. Their value is different. They represent a set of conclusions, arrived at through contemplation, ceremony, and generations of careful observation about the deepest character of reality. And when those conclusions occasionally echo what the most advanced physics of the 21st century is cautiously beginning to suggest, that reality is relational, that consciousness may be fundamental, that the universe operates on timescales and scales of complexity that make human measurement look like a keyhole view, the echo is worth noting. Not as proof, as pattern, as the recognition that certain questions, asked with sufficient depth and honesty from any direction, tend to arrive at the same horizon. In 1513, an Ottoman admiral and cartographer named Piri Reis compiled a map of the world. He described it as being based on older source maps, some of them, he wrote, dating back to the time of Alexander the Great, drawn from charts whose origins he could not fully trace. The map itself, drawn on gazelle skin, shows the Atlantic Ocean, with the coasts of Europe and Africa on the right, and the coasts of what is unmistakably South America on the left. The rendering of South America's eastern coastline is, given the date of composition, remarkably accurate, better, in some respects, than maps produced in Europe decades later. That alone would make it a curiosity. But what makes the Piri Reis map a subject of enduring debate is a long coastline extending along the bottom of the map, a landmass running east to west below South America, with bays, inlets, and geographical features that do not match any known coastline that was accessible to any sailor in 1513. They do, however, resemble the coastline of Antarctica. Antarctica was not officially discovered until 1820, more than 300 years after Piri Reis compiled his map. More specifically, the coastline of Antarctica beneath its ice sheet, its subglacial topography, was not mapped with any accuracy until the seismic surveys of the International Geophysical Year in 1957 and 1958. The ice sheet that covers Antarctica is, in some places, several kilometers thick. Without instruments capable of penetrating that ice, the coast beneath it is invisible. The mainstream archaeological response to the Piri Reis map's southern landmass has been careful and measured. Some scholars argue that what appears to be Antarctica is actually a distorted rendering of the southern tip of South America, stretched and repositioned by the map's non-standard projection. Others suggest it represents a speculative depiction of the Terra Australis Incognita, the hypothetical southern continent that European geographers had long predicted must exist to balance the land in the northern hemisphere. Both explanations are plausible, neither is proven. The alternative interpretation, that the map was copied from a source that had access to knowledge of Antarctica's subglacial coastline, is treated as the domain of pseudo-archaeology by most mainstream scholars, and the dismissal is understandable. Extraordinary claims require extraordinary evidence, and a map that raises questions is not by itself extraordinary evidence of anything beyond the questions it raises. But what is worth noticing, and this is the thread the documentary has been pulling since the first chapter, is the pattern of response. When anomalous evidence appears, the institutional response is almost always to find an explanation that preserves the established timeline, rather than to treat the anomaly as an opportunity to question the timeline itself. This is not necessarily wrong. Most anomalies do have conventional explanations. Most apparent mysteries resolve into misreadings or coincidences when examined carefully enough, but not all of them do, and the Piri Reis map has been examined carefully for more than a century without producing a consensus explanation for its southern landmass. The debate continues. The map exists. The resemblance to Antarctica is visible. Whether it is meaningful remains, like so many of the questions this documentary has raised, genuinely and honestly open. The interesting thing about maps that shouldn't exist is not necessarily what they prove, it is what they suggest about how much of the territory remains undrawn. In 1962, a historian of science named Thomas Kuhn published a book that changed the way educated people think about how knowledge advances. The book was called The Structure of Scientific Revolutions, and its central argument was both simple and deeply subversive of the image science had constructed for itself. Science, Kuhn argued, does not advance through the steady, cumulative accumulation of facts. It advances through revolutions, discontinuous, disorienting upheavals, in which one fundamental framework for understanding a field collapses and is replaced by another. He called these frameworks paradigms, and he demonstrated, through careful historical analysis, that the periods between revolutions are characterized not by open-minded inquiry, but by what he called normal science, the patient elaboration and defense of the existing framework, the explanation of anomalies through increasingly complex ad hoc adjustments, and the active marginalization of researchers whose work threatens the reigning model. The history of science confirms this pattern with uncomfortable consistency. When Ignaz Semmelweis, a physician working in a Vienna maternity ward in the 1840s, discovered that puerperal fever, a disease killing roughly 10% of women who gave birth in hospitals, was being spread by doctors who went directly from performing autopsies to delivering babies without washing their hands. His data was clear. In the wards where hand-washing was introduced, mortality dropped immediately and dramatically. The evidence was unambiguous. The medical establishment rejected it, not because the data was bad, because the implications were unbearable. Semmelweis's discovery meant that doctors were killing their patients. It meant that the most educated, most respected practitioners in the field were vectors of disease rather than agents of healing. The paradigm that defined what it meant to be a good doctor could not accommodate that conclusion. Semmelweis was ridiculed, professionally isolated, and eventually committed to an asylum, where he died at 47, reportedly from the same type of infection he had spent his career trying to prevent. The medical community adopted hand-washing as standard practice roughly 20 years after his death, when Pasteur's germ theory provided a theoretical framework that made the practice make sense. The practice was vindicated not when the evidence was strong enough, the evidence had been strong from the beginning, but when the paradigm had shifted far enough to make room for it. Alfred Wegener proposed continental drift in 1912, arguing from the geological and fossil evidence that the continents had once been joined and had drifted apart over millions of years. The mechanisms he proposed were incomplete, and the establishment used that incompleteness as grounds for comprehensive rejection. He was mocked at professional meetings. The idea was considered so far outside the bounds of respectable science that for decades, proposing it risked one's career. Plate tectonics, the complete and verified theory that confirmed Wegener's core insight, was not accepted as mainstream geology until the 1960s, half a century after he first proposed it, and decades after his death. The Big Bang itself, the very model now presented in textbooks with serene certainty, was initially a target of institutional skepticism and aesthetic displeasure. Georges Lemaitre, a Belgian Catholic priest and physicist who proposed in 1927 that the universe was expanding from a primordial point, met resistance from Einstein himself, who told him his physics was correct, but his physical insight was abominable. The name Big Bang was coined by Fred Hoyle, a steadfast opponent of the theory, as a derisive label intended to make it sound absurd. The label stuck. Long after the theory it was meant to mock had become the foundation of modern cosmology. What these cases share is not the incompetence of the scientific community. The scientists involved were, in most cases, intelligent and well-intentioned. What they share is the structural feature that Kuhn identified. Paradigms do not just organize knowledge, they filter perception. They determine what counts as a problem worth solving and what counts as an anomaly to be explained away. They create professional and social incentives that punish deviation and reward conformity, and they produce a gap between what the evidence suggests and what the community is prepared to accept that can persist for decades. Science is the most reliable method ever developed for understanding the physical world. It is not, however, immune to the sociology of the institutions that practice it. Paradigm resistance is structural. It happens without malice, without coordination, without any individual actor deciding to suppress the truth. It is the emergent behavior of a community organized around a shared framework, a community that, like all communities, tends to protect the assumptions that hold it together. But there is another kind of knowledge suppression. It is less philosophical, more deliberate, and better documented than paradigm resistance. It does not require a conspiracy. It requires only institutions, with incentives powerful enough to outweigh the ordinary commitment to truth. In the 1950s and 1960s, cigarette companies conducted internal research on the health effects of tobacco. Some of that research confirmed, with increasing clarity, that smoking caused cancer. The companies did not publish the findings. They funded alternative research designed to produce doubt. They hired scientists to testify that the evidence was inconclusive. They lobbied against regulatory action. They ran public relations campaigns, suggesting that the science was contested when, within their own internal documents, the conclusion had already been reached. This strategy, manufacturing doubt about established findings, continued for decades, during which time hundreds of thousands of people died of smoking-related cancers, while the companies publicly insisted the evidence was uncertain. This is documented. It is not speculation. The internal documents were eventually produced in legal proceedings, and they are publicly available. The strategy of manufacturing doubt was explicitly described in memos written by tobacco company executives in plain language. The same pattern, executed by some of the same public relations firms, was deployed by the fossil fuel industry against climate science beginning in the 1980s, when several major oil companies, including ExxonMobil, conducted their own research on climate change that confirmed the scientific consensus, and then chose not to publish it and instead funded campaigns to create public confusion about the science. Again, this is documented in internal records, congressional testimony, and peer-reviewed research into the sociology of science denial. Neither of these examples is cosmological, but they establish something important: the suppression of inconvenient scientific knowledge by institutions with sufficient incentive is not a paranoid fantasy. It is a documented historical phenomenon, confirmed at the highest levels of legal and legislative scrutiny. The mechanism exists, the precedent exists, the motivation, the protection of institutional, financial, or political power from findings that would threaten it, exists in every field where the implications of discovery are large enough to matter to those who hold power. The question the narrator does not answer, and does not pretend to answer, is whether similar mechanisms operate in cosmology or consciousness research. The honest position is, the evidence for deliberate suppression in those fields is thin to non-existent. What exists is more subtle. The systematic underfunding of research into questions whose answers might be disruptive. The professional disincentives for researchers who work at the margins of established paradigms. The institutional habits that make certain questions seem less serious than they might actually be. This is not a conspiracy. It is the ordinary operation of institutions designed to perpetuate themselves. It produces a slow, structural narrowing of what questions get asked, what results get published, and what knowledge gets communicated to the public, not through censorship or malice, but through the accumulated weight of incentive, habit, and the path of least professional resistance. The result, over time, is a public understanding of science that lags behind science's own frontier, not because anyone chose to deceive, but because the machinery of knowledge production, like all machinery, tends to move along the grooves already worn into it. Follow the money. It is not a sophisticated analytical tool, but it is a reliable one. What a society chooses to fund is what that society, at an institutional level, considers worth knowing. And the allocation of research funding in science reveals a set of priorities that do not perfectly match the hierarchy of open questions. The search for extraterrestrial intelligence, SETI, was funded by NASA for several years before Congress defunded it in 1993, with a vote that included some mockery from the floor. The project was described as a waste of taxpayer money, the search for little green men, dismissed with the easy condescension available to any politician willing to trade rigor for laughter. Since that defunding, SETI has operated on private donations and philanthropic grants, a fraction of the resources available to other areas of space research. This is the scientific program tasked with answering what may be the most consequential question in the history of civilization. Are we alone in the universe? Running on a budget smaller than many university departments. Consciousness research occupies a similarly precarious position. Despite being arguably the deepest open question in science, the one most directly relevant to understanding what human beings actually are, it receives a tiny fraction of the neuroscience funding that goes toward understanding the brain's clinical and pathological functions. The National Institutes of Health, the largest funder of biomedical research in the world, does not have a dedicated program in consciousness research. The programs that exist are small, often housed in philosophy departments rather than neuroscience programs, and chronically underfunded relative to the scale of the question. And then there is Göbekli Tepe. In the hills of southeastern Turkey, a Kurdish shepherd found a carved stone in 1994. Archaeologist Klaus Schmidt began excavating the site the following year, and what he found beneath the surface rewrote a foundational assumption of human history. The site consisted of massive carved stone pillars, some weighing up to 20 tons, carved with animals and abstract symbols of extraordinary sophistication, arranged in circular enclosures on a scale that dwarfed anything previously known from that era. The date of the construction, approximately 12,000 years ago. This predates Stonehenge by 7,000 years. It predates the first writing by 6,000 years. It predates the development of agriculture, which had been the assumed precondition for the kind of coordinated social organization required to build monumental architecture, by at least 1,000 years. Göbekli Tepe was built by hunter-gatherers, people who, according to the prevailing historical model, should not have had the social complexity, the organizational capacity, or the symbolic culture to produce anything like it. The implication is not minor. If nomadic hunter-gatherers could build a site of this complexity and scale, the assumption that civilization arose with agriculture, that agriculture was the precondition for everything that followed, requires fundamental revision. The first chapter of human civilization was not written when people began farming. It was written earlier, in ways the archaeological record has not yet fully revealed, because the sites that might reveal it have not yet been excavated, or have not yet been found, or have been found, and await the funding and institutional will to investigate them properly. Göbekli Tepe was buried intentionally by its builders 12,000 years ago, covered under tons of soil in a deliberate act that preserved it until the 20th century. It waited. The questions it raises have been waiting too, in the slow queue of underfunded, institutionally inconvenient research that characterizes the frontier of knowledge when the frontier threatens to revise something important. What else is buried? How many first chapters remain unwritten because no one has yet funded the excavation? Pause here for a moment and take inventory. The universe is made of something we cannot see, cannot touch, and cannot explain, and that something constitutes 95% of everything that exists. The expansion of space is accelerating, driven by a force whose theoretical prediction is off from its measured value by a number so large it breaks the capacity of intuition. The two most accurate theories in the history of science are incompatible with each other, and the resolution of that incompatibility has been the central unsolved problem of theoretical physics for nearly a century. At the subatomic level, reality behaves differently when it is observed, and the meaning of that behavior has been argued about without resolution since the experiment was first performed. The beginning of the universe is inaccessible to current theory, and the alternatives proposed to explain it suggest a cosmos that has always existed, cycling through births and rebirths on timescales that dwarf any religious or cultural imagining of eternity. The galaxy is silent. Decades of careful listening have produced one unexplained event, and an otherwise unbroken absence of signals from any civilization anywhere in a galaxy old enough to have produced millions of them. The most sophisticated statistical reasoning about our own place in the human timeline suggests that the optimistic version of humanity's future, a long, expanding interstellar civilization, may be statistically improbable. The hardest problem in science, why any physical process gives rise to subjective experience at all, remains unsolved after decades of intense investigation by brilliant minds working with extraordinary precision. Ancient civilizations tracked the sky with a precision that continues to generate genuine archaeological debate. A 500-year-old map contains features that have not been satisfactorily explained by conventional cartographic history. A 12,000-year-old site in Turkey required the complete revision of one of the most fundamental assumptions about the development of human civilization. These are not the findings of alternative researchers operating at the margins of knowledge. They are the acknowledged, published, peer-reviewed open questions of mainstream science and scholarship, sitting in the center of the fields that study them, waiting for the frameworks that will eventually make them tractable. The classroom poster had 8 planets. None of these questions fit on it. None were omitted because they were trivial. All were omitted because they were too large, too unresolved, too genuinely threatening to the sense of order and completion that an educational institution is designed to project. You came here, at some level, because you suspected the map was incomplete. The suspicion was correct. The map is incomplete in ways that are formally acknowledged by the very institutions that produced it. The incompleteness is not a secret. It is just rarely communicated with the gravity it deserves. It deserves considerable gravity. Johannes Kepler spent years trying to fit the orbits of the planets into a system of nested Platonic solids, the 5 perfect geometric forms that the ancient Greeks had identified as the shapes of the cosmos. It was an elegant idea, a beautiful idea, and it was wrong. The data refused to cooperate. The orbits were not circles inscribed in perfect polyhedra. They were ellipses, slightly imperfect, slightly flattened, and the imperfection was not a measurement error to be polished away. It was the truth. Kepler accepted it. He discarded the beautiful model and followed the data, and in doing so, produced the laws of planetary motion that Newton would later explain and Einstein would later refine. The bravest thing Kepler did was not the discovery, it was the willingness to let the discovery destroy something he had loved. Vera Rubin spent years presenting data that the establishment was not ready to accept, to audiences that were not always willing to take her seriously. She continued. The data held. The ghost that held the galaxies together was real, whether anyone was prepared to acknowledge it or not. She was prepared to follow the evidence wherever it led, regardless of the professional and personal cost of asking questions that the paradigm had not yet made room for. Einstein spent the final 30 years of his life in pursuit of a unified field theory, a single equation from which all the forces of nature could be derived. He did not find it. He died with a notebook on his desk, equations half finished, the search incomplete. That unfinished work is sometimes cited as evidence of failure. It is more accurately understood as evidence of the scope of his ambition, a mind that had reshaped physics twice, refusing to stop reaching simply because the next reach was difficult. The common thread in all of them is not success. It is posture, the willingness to hold a genuinely open question without forcing it closed, to sit with uncertainty as a productive state rather than an emergency to be resolved, to follow evidence into uncomfortable territory without requiring the destination to be comfortable before the journey begins. This is what intellectual courage looks like from the inside. It is not dramatic, it is quiet and patient and often lonely, and it produces, when it produces anything at all, not the closing of questions, but the opening of better ones. The universe does not reward the mind that insists on certainty. It opens, slowly and reluctantly, to the mind that can bear the weight of not knowing, and keeps asking anyway. In 2004, the Hubble Space Telescope was pointed at a small region of sky in the constellation Fornax, a patch of darkness that appeared, to any ordinary observation, to contain nothing at all. The telescope held its gaze on that emptiness for nearly 400 consecutive orbits, accumulating light over 11 days of exposure. The resulting image, when processed, revealed approximately 10,000 galaxies, each one a collection of hundreds of billions of stars, each one separated from its neighbors by distances that light would require millions of years to cross, each one containing, in statistical probability, billions of planets. The entire frame covered a region of sky smaller than a grain of sand held at arm's length. The observable universe contains approximately 2 trillion galaxies. The total universe, the space beyond the cosmic horizon, the regions from which light has not yet had time to reach us, may be unimaginably larger. The number of stars in the observable universe alone exceeds the number of grains of sand on every beach and desert on Earth by a factor of approximately 10. The number of planets exceeds the number of stars. The number of possible configurations of matter and energy and time within that space exceeds any number that language can usefully contain. And humanity, on a small rocky planet, orbiting an ordinary star, in a quiet corner of one unremarkable galaxy, has spent a few thousand years developing the instruments and the mathematics to begin asking what it all means. The questions this documentary has followed, through invisible architectures and quantum strangeness, through the before time of creation and the knife-edge calibration of the physical constants, through the silence of an enormous sky and the unsolved mystery of what it means to experience anything at all, through the stone monuments of ancient builders and the buried questions of underfunded inquiry. These questions are not distractions from the main story of science. They are the main story. The resolved chapters are the footnotes. The open questions are the text. The universe is not finished being understood. It may never be finished being understood. The edge of the known is not a wall. It is a shoreline, and the ocean beyond it has been there all along, indifferent to whether any mind was ready to sail into it. The universe is not what they told you in school. It is stranger, deeper, older, larger, and more intimately connected to the fact of your existence than any classroom diagram has ever suggested. What it actually is, that is still being discovered, and the discovery belongs to anyone willing to keep asking.